Hello, here is my machine learning project. It's called Manipulating Phase of the Fourier Transformation for Pattern Recognition in Prostate Cancer in MRI. I am Nicolas Monera. And okay, let's begin now the explanation. So, to begin with, the Fourier transformation decomposes a given signal into its frequential components, that is to say, magnitude and phase. And in the case of an image, phase has some particular interpretation. Back then in the 80s, Oppenheim published an article that has this example that I have right just here in the middle. Here we have at the left a random image, and then we have the same random image just reconstructed by just using the phase of the transformation and discarding the magnitude or leaving just one constant magnitude. The thing that we see here is as powerful as with just the phase, we still can see the objects. This means that phase has the spatial support of the image, and it can be as powerful as, for example, in magnetic resonance image. You can use this spatial support to characterize tissues that are healthy or abnormal. And let me elaborate a little bit more about this, and is that magnetic resonance image is a direct application of the Fourier transformation, as you have these waves at direct frequency, at different frequencies going around the tissue. And the thing is that the response of healthy tissue should be different than the ones that the response you would get from an abnormal tissue. So in that sense, we would like to capture this spatial support that represents the healthy and the abnormal tissue for a problem like getting samples of or patches of magnetic resonance image, in this particular case for prostate resonance image. So here what we propose are two methods that we're going to compare. The first one uses the Dirichlet distribution, and the second one uses the power of neural networks to get to a phase estimation. So what do we want? What we want is that we know that the Fourier transformation decomposes the signal into magnitude and phase, and what we want to do is to estimate a phase matrix that gets a spatial support that uncovers those patterns that are rare, that are maybe hidden, or that are not that visible on the image. So I'm going to elaborate first about the Dirichlet approach. And we have here our MRI patches. On the top we have the ones for abnormal tissue, and at the bottom the ones for normal tissue or healthy tissue. So for each patch we compute the Fourier transformation, we get its phase. Then for the phase stack, that is here. Okay, getting back to recording. What we have is that for the phase stack, what we do per phase matrix is to tile it. In our case, we selected 3x3 tiles, and that's because we want the tile to be as small to make data to distribute as Gaussian or as something that we could parameterize. And as you can see here, phase data is really noisy. Like you don't a classic dimensionality reduction technique won't work on this kind of noisy data. So we have to do this kind of things to make it work. And what we do is that here is the stack, one kind of 3D view, and as the spatial location of phase is important, and with spatial location I mean like the point where each pixel is located. So I can't just take all those tiles and try to do machine learning upon the tiles without taking into account the place where they are located, the location within the matrix. So what we did was to clusterize those tiles that are in the same spatial location. So we take all the tiles that are on the same spatial location, and what we did was to create one Gaussian mixture model to model this data. In our case, it's a Gaussian mixture model of dimension 9, as we took 3x3 patches of 3x3 in resolution. And what we do to reduce this data is to take the mean with the mean of the distribution with the highest value of lambda or the highest weight. So in that sense, we are able to reduce the data, and that's how I say mean per pixel. So this mean per pixel is just selecting this the highest peak of the distribution, and in that sense we get a phase matrix for what I said, cancer and healthy tissue. Second approach that we wanted to try out is about neural networks. So for using neural networks, what we have here is that we have our training batch. The training batch is transformed by a de Fourier transformation, where we get magnitude and phase spectrum. Phase spectrum is discarded, as what we want to learn is this matrix. So we take each pixel of the phase matrix and we leave each pixel as a variable that we're going to learn. So what we do here is that we compute the inverse Fourier transformation of the magnitude and this variable. The idea here is to process all the batch images with the same phase, as what we want is that this spatial support pops out those patterns that we want to capture. Then it goes to a feature extraction layer that in our case is carried out by the DenseNet 121. And then after features are extracted by using this architecture, we use this top layer, where what we do is to flatten the last layer of the feature extractor. Then with a hidden layer we leave some room for the network to learn some patterns to classify well between healthy and cancerous tissue. And at the end we get the binary classification output that is done by having one output layer with a sigmoid activation function. So as results, first thing is to talk about the dataset. So for the dataset, we use the ProstateX dataset, which has data for 95 lesions. That means 95 patients with cancer, and we don't have like images of persons who don't have any kind of, or who don't have any of normality. So what we did was that as we have the central coordinate position, what we did was to take a patch of 30 by 30 pixels. In some cases it was bigger, but then they were resized to 30 by 30 pixels to leave all images to the same resolution. And after we took those patches with cancerous tissue, what we did to get data from the healthy class was to take one patch per patient that was as far as possible from the one that we have on for the cancerous tissue. So this means that we're going to get 3 estimators of phase that we're going to use to preprocess data for this dataset. And all patches in total are 150, from 150 to 200 patches in total. So first we have this assessment of visual results. What we have here is that these are some patches. This one in green is for a healthy patch, or a patch containing healthy tissue, and the other 2 ones are from patches that have abnormalities or cancerous tissue. These are the original patches on the first row. On the second row we have the ones corresponding to the reconstruction using the cancer estimator provided by the Dirichlet approach, and this is how it looks like. Then using the one on the healthy, this is how it looks like, the reconstruction of the patch. And then from the neural network, this is how it looks like. The neural network was, like some remarks, some comments, was a bit tricky because in some cases it didn't converge, and I tried to use the data without augmentation, as I wanted to fit this phase to the raw data without doing some transformation or synthetic data, but the model just didn't work with such a small number of samples, so I had to do data augmentation. And data augmentation changed the training set from 120 images to 1000 to 200 images, so there were a lot of synthetic images, and that might be harming the performance, and also that network wasn't able to overfit, and a lot of things on this architecture were tried, experimenting with different less functions, different optimizers, different ways to use the top layer, and things are still that tricky. So this is what happened with the neural network. Hopefully, with more data, we would get a better estimation by using this kind of approach. Because by now we're getting harmed by using those synthetic data that we are seeing, that what we're uncovering here is not as it's supposed to look like. And these are the results of classification. But before assessing those results, what we did was the following. We took the dataset, and the dataset was pre-processed by using the three estimators that we got, and with those, meaning that we get 4 datasets, one without processing and one processed by this phase matrix and other processed by this one, and so on. With those sets, what we did was to use the 7030 scheme to do a transfer learning on the DenseNet 121 architecture, but on this case for classification purposes. And the results that we're seeing down there are with the testing subset. Those experiments were computed not in Keras. I used Keras for this model that I have up here, and then here I used Fast AI, which is built upon PyTorch, and it's a library that wraps up some of those trickery and things that provide the state-of-the-art performance. So we wanted to get the best performance as possible, and this is how we got. So the dataset without preprocessing, we get a sensitivity of 94, specificity of 88, and accuracy of 92. With the cancer estimated phase, we have sensitivity of 1, specificity of 92, and accuracy of 97. And with the healthy, this one here, proposed using the healthy phase from the Dirichlet method, we get sensitivity of 1, specificity of 96, and accuracy of 98. And with neural networks, with all the remarks I've made, well, performance was just not good. Or for approaches were trained under the same conditions. I mean, 50 epochs, learning rate of 10 to the minus 4, and the partition of training and test subsets are on the same subjects for these 4 datasets to provide a fair comparison between them. So thank you so much. This was the project, and one advance of my thesis project for the master's degree. So thank you so much.